Hello everyone, it's March 30th. Let's do it today. Well, we didn't do very well yesterday because I think it's because it's very late and my mind is not working well. So today we're going to do it early and try to see if we can hit it good. I just learned that the latest SpaceX test flight SN11 exploded. I was trying to find some videos online to see how it exploded, but it seems like it was in a very bad condition. There was no good camera angle. So we'll wait for that. We'll wait for that. I'm interested in see how that one exploded. I mean, they have exploded how many? I think since SN8, right? Every single one has exploded. Interesting. All right. Anyway, let's take a look. What we have today. We have Russian doll envelopes. Okay. They're given a 2D array of integers. I call them envelopes, where we have W and H represents the width, okay, and height of an envelope. One envelope can fit into another if and only if both the width and height of one envelope is greater than the width and height of the other envelope. Return the maximum number of envelopes you can Russian doll. Not can you Russian doll. You can Russian doll. Put one inside the other. You cannot rotate the envelope, so it has to be used as is given. So we have a 5 and a 4, so the width is 5, height is 4. If both is greater than, so 6 and 4, it does not fit, right? Because the height is not big enough. 6 and 7, now this can fit into 6 and 7, and this can fit into any one of these. We can Russian doll is 3. Oh, we want to put them together. Okay, so this one will be in here, this one will be in here. This will be 1, which means just nobody can go into anybody else. Okay, it's pretty clear, the question. So sort it, right? That's the very natural way of thinking. We sort it based on width or based on height. Doesn't matter. I think we sort it based on width first, and if width is the same, we sort it based on height. So this will give us, if we take a look at the first one, if we sort it based on width, so it's going to be 2, 3 first, right? 2, 3 go first, and then 5, 4. And then 6, 4, 6, 7, and then we say second level when based on height. So we're gonna go 6, 4 first, and finally 6, 7. And then we're gonna go from front to back. So we go 2, 3 is the first one, is the smallest in all dimensions, and then we check the next one, and then if the next one, actually this one, is bigger, right? Then we fit, right? And then if it's not, then we just keep looking. So we always try to fit the smallest, right? We try to fit the smallest to the smallest possible envelope that can fit it. So we go here, and then we go next one. If the next one has some dimension is the same, we just keep skipping until we find the first one that does fit. And then we're gonna fit together or move the pointer here, and then keep going. So now pointing here, we have 2, right? And then this one will find next one's here, doesn't do because they're not the same for the next one. Okay, so I think this is an easy question. Well, I mean, it's an easy one, which means it doesn't count as a revenge from yesterday. But nonetheless, we are going to solve it, so that's good. Kind of also refresh on how to do sorting on 2 levels. I shall know how to do this. It shouldn't be too hard. Sorting, just provide a key. Yeah, provide a key. So we're gonna say envelopes.sort, right? And then we say key equals lambda top. It's actually not tuple, but we're gonna just call it top. And then gonna be top 0, we saw the first, and then top 1. Actually, I think this probably is a default sorting. We just, just to make it explicit, right? Let's just make it explicit. So we sort it, and then we're gonna say, left and right. No, we're gonna say front and back. Front and back will be 0 and 0, right? And then, oh no, actually it's gonna be 0 and 1. And we say, and the result is going to be 1, right, to start with. And we say while back is smaller than len envelopes, right? Then we do front if envelopes back. That's called FMB. It's too many words. No. And actually, okay, I see your point. Front and back, people have different idea about front and back. Let's just call it left and right. L and R, right? We'll just call it left and back. So this can be right. I'm gonna say right 0 is larger than envelopes left 0 and envelopes right 1 is larger than envelopes left 1, right? So that means we can fit when the call res plus equal 1 and left equals right, else right plus equal 1, right? And then eventually we're going to return the res. I think this probably is it. The two test cases. First one is this. Then the answer is 3. Fixed all the commas. Oh, fixed it wrong. The second test case is gonna be this. Oh, what the hell? Right there. That's 1. Okay. Fix the commas. This one will be envelopes. This will be max envelopes. Envelopes. All right. Check it. What is this? Did I have to put a parentheses? Oh, you have to put a parentheses. Okay. I thought it can automatically, and doesn't matter. All right, so you want to test something else? Shouldn't. I think the logic's pretty clear. Let's try. If we fail, we test something else. Ugh, we does fail. That is interesting to say the least. Okay. Something is wrong, and we don't want to see it. I'm trying to figure out what was wrong. All right, so we're gonna just refresh it. Then I'm gonna remove the test case with the wrong answer. Yeah, let's throw something in it. Envelope dot length. Let's try one of them. Is that like the? This is like the edge case. Edge case pass. Okay, so it's not that. Let's see. Usually it could be. Oh, I think it's the exit, right? It's the exit. Hold on, let me think. Is it the exit? So like the last one, and then we compare. We keep incrementing R every single time. And if it does not fit, because every time we change That should be fine, right? I mean, I don't know, 5, 5. This one should give us 1 as well. I'm just randomly testing some stuff. I'm just trying to see. Yeah, I'm just trying to see what gets. This one shall be 2. Whew. What is the issue here? The maximum number, right? That is the maximum. Oh, I think I know. Wow, is that the thing? Let's just do this. Yeah, I think I know. Wow, this actually made the question more complicated. Is this 1 or 2? Oh, no. This should be 4. This is 2. This is 2. Ah, that's not what I thought, right? It's, yeah, the maximum Russian doll. Okay, so yeah, this is 2. If you're saying that there are some situations that this algorithm, this is basically like a greedy algorithm, right? We always try to put the smallest into it. Why would that be wrong? No, I won't be wrong. If I always try to put the smallest into it, let's break this. I also suspect maybe the sorting is wrong. That could be a thing. So let's say we sort it differently, right? Let's put this one up front. See what's gonna happen. So put this one up front. Still accurate. And then we say the envelope.length is 1 to 5,000, so there's no edge case on empty. What could be the issue here? So we sort, right? We sort, and everything will be based on the width, right? Everything will be based on the width, and then height. When width is the same, and then it's going to be height. Oh, I suddenly think about one case that I might overlook. Like this, 1, 1, right? And then I can get into 2, 2, or I give it 2, 100, right? And then, no. No. I'm trying to say, like, because we are choosing them with a small. Yeah, we're always choosing a small. It shouldn't be an issue here, right? But like, huh. Yeah, so we are not choosing the things. What could be the problem? Man, we need to like generate random stuff to. I don't know, man. I mean, there's one way we can do. We can do it like stupid way, just O(n) squared for this. Well, actually, that's not easy to do. I mean, you don't know. It will have to. If they are the same, and we get another one. it shouldn't, right? We always keep it the smallest. Always keep it the smallest. We always keep it the smallest. Russian doll it. I don't know, man. This is strange. I think I'm just playing around with it at this point. Just trying to see if there's any discovery just by playing with it. I don't know. I mean, I'm trying to see if luck hits me. Man, luck does not hit. Luck does not hit. This is a 1, right? We have encountered all the situations. Why would it be wrong answer? I want to see. I want to see, like, what situation that we did not consider. Right? We say R need to be smaller than the length of all the envelopes. And we say the current envelope, we're looking at R, right? I want to compare current envelope width to width and length and height to height. And if it does not contain, then we jump R forward. If it does contain, then we say we move left to the R position, yes, because that will be our base we want to do for the next one. All right, and then next one does not fit, does not fit, does not fit. How is this not correct? I'm giving up on this. I'm gonna try to find the test case that failed us. What is the test case? Oh wow, this is considered a hard problem. Which means there's a weird test case that I still don't want to see. I don't want to see. I don't want to see. What the heck? What's the situation that you did not consider? The maximum number of envelopes you can Russian doll. Right? The maximum number. I mean, the only possibility is this solution will not generate the maximum number. Right? That's the only possibility. So read the question again. You're given this, right? Width and height. And you cannot rotate the envelope. So it has to be given as it is. And it can fit into another if and only if both the width and the height of one envelope is greater than that of the other envelope, right? So we say, if we sorted it, right? And let's think like dynamic programming. Okay, for a certain envelope, I know the maximum that I can hold, right? And then I'll look at the next one. So the next one, I say, if I'm bigger than you, then the maximum I can hold will be you. The maximum you can hold plus yourself. Is that correct? Yeah, I think that's correct. And if I cannot hold you, then I need to find the one that does hold, that I can hold, and I'll put the maximum that it can hold. How is that different from this one? because I iterate through, right? I sorted it, I iterate through. I starting from the smallest, right? And then I say the smallest can the Russian dot 1, and look at the next one, and the next one is bigger than me, then it shall hold me, so that one becomes 2. If that one is the same as me, and then that one shall also hold 1, right? And then we keep going to the next one, and then the next one is the same as me, is the same, so it can choose. I mean, everyone, why would you not want to contain the smallest one? You always want to contain the smallest one, right? Because you want to make yourself bigger. If I cannot contain the one right in front of me, then I think in my solution, I just don't consider that. Because I only want the greedy, right? I only want to be contained by the smallest possible that can hold me. And everyone is the smallest possible that can hold me. Well, I think what it's saying is it is possible. Is that like it's possible for something that's not the smallest? But if it's not the smallest, then if it can hold, if it has the same dimension as me, then it shall be able to, if I can hold that, I can hold myself too. I don't understand. I don't understand. I want to check. Okay, I'm checking the wrong answer. Okay, what is this? All right, I'm checking the answer. Well, not really checking the answer. I'm checking the expected 5. I want to see what situation that I have not considered. Okay. All right, what do we have here? 2 100, 3 200, 4 5, and 5 5 6 6. Okay. Can we sort it? Yeah, I think we can sort it. Let's just print envelopes. So that's the sorted version, right? So 2 100, 3 4 5 5 6 7. This can contain this. This can contain this. That's 3. Cannot. 4. Cannot. 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 Oh. Oh, now I see. This limited us. This limited us. I could choose from here to here. And then from here to here. Ah, how did you not think about that? I was close, all right? I was close. I was thinking about this. I was very close. It's just yes. Oh, yes. That is the issue. Okay. 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 That's fine. That's fine. Okay. Interesting. So we cannot do immediately. That will cause fail. How about dynamic programming? So like this, if it is, so we can do dynamic programming. So up to here, it should still be the same, right? And this one, it does not contain here, so I need to go front, trying to find, because this one will, if this one is equal to this, then there's no chance. We just keep moving. Now if the first one is larger, then we're going to check the second one. The second one is not, so this one, the maximum it can hold here will actually be this, right? So it can hold this. So this one will be 3. And then this one is the same, so I cannot. Oh, actually, say if it's the same, so this one will be 3 too. No, we have to look, and then we find that it's here. So this is actually 4. This is 4, and coming here we cannot do. So we look in the front, right? And then this one will be 4 as well. Now here, this one cannot hold, and then I look to the front. So this one was 4 as well, and then this. This cannot hold this, so we have to go front. So it's bigger than this. No, this cannot do. Is this one bigger? So no, no, here, right? So this one is 3. So this one is 4 as well. And now look at this. We can hold. So this one becomes 5. So what the dynamic programming can work, but that will be O(n) squared. That will be O(n) squared. But we have 5,000. O(n) squared, I think it's going to time out. All right, even if timeout, let's write a correct solution first, even if it's going to timeout. So we still sorted, right? We still sorted, and we are going to say for I, width and height in envelopes. Yes, we do need to enumerate envelopes. Actually, res even 1. I don't like it. Let's just say for I in range 1 to land envelopes, right? So currently I am here, right? 1, and then I want to have a DP as well. DP equal to 0 times land envelopes. So the envelopes use it twice. So let's put this as a. Why you always say this envelopes? So this is gonna be n, and I'm gonna change DP 0 equals 1 because that's the first thing. So I'm going to be for range this, right, to n. And we say if envelopes I 0 is larger than envelopes I minus 1 0, and the same thing again, but this one will be 1. So if this, then dpi equals dpi minus 1 plus 1, right? Now else, so one of them doesn't match, so we're gonna look back, right? Look back. Now when we look back, we have basically 2 situations. One is when we look back, right? Either the height or the width that doesn't satisfy. So we're gonna look back to find the first one that does satisfy. We can use binary search to find the satisfying width, but to find a satisfying height, right? We still need, but we probably can't. Yes, we shall use binary search for this. How do we do a binary search based on, I mean, it's a two-dimensional. We can manage. I think it's possible to manage it. Yeah, we know we can do binary search because these are sorted. Like when these are the same, so we can immediately jump. So when we all we need to do is to find the one that's one smaller than us, right? We probably can even do this. Huh. Hold on. It might be possible. So we turn this into a dictionary, right? With the width as the key and the height is going to be a list, right? So whenever we got stuck, so hold. Then if you do that, so what I'm thinking is, like for this thing, yeah, let's turn this into something like this, right? So we have 2, it's going to be 100. 3 is going to be 200, right? 4 is going to be 300, and 5. Now we're going to sort it as well. So it's 5 is going to be 250, 400, 550, right? And then 6 is going to be 360 and 370, and finally 7 is going to be 380, right? So that is the data structure we're going to use. So it's a dictionary. So what we do, we're going to iterate from 2 to 7, right? And for each one, we can also put a dummy. Put a dummy to make things easier. So the dummy is going to be 0, 0. So everybody, so it can be included in anything. So we're going to, from 2 to 7, right? And then in 2 to 7, every time we look for the smaller one. So the current key is 2, so we're going to look for the smaller one, which is the one above it. So it's actually, we're going to do the keys, right? The keys is going to be 0, 2, 3, 4, 5, 6, 7. And we're going to iterate through the keys from 2 to 7. So everything is going to look one back, the key. And in this key, right, what we're going to try to find is the value that is just smaller than my current value. And we use binary search for that. So current is 100, and binary search to find, oh, we don't even need binary search, right? All we need to do is to make sure that there's something in there that is smaller than me, right? That's it. So we only need to look for the min, right? So here too, I have 100. So I look for the min, and the DP, right? And the DP is going to be, for this one, we're going to put -1. No, we're going to put 0 for the first one, and then 0, that's for 2, 3, 4, 5, 6, 7, right? So from 2 to 7, so we'll look at 2. 2, we're going to look 1 ahead, and then we'll look into it. We'll get the min value is 0, and my value is, oh, is it min value? Or is it going to be like a 2? Let's just walk through. I mean, this is an easy case, right? So when we consider 2, let's just see how the DP change. So like the DP will be what? Like the maximum dose you can hold But we do have to consider, we have to consider like different, right? Different things, they will hold different things. For example, 5250 will have a different DOL compared to 5400, right? And when we go from 360 in, we cannot go for 250. We have to go for 360. We can only go for 250, and 370 we can only go for 250 as well. But let's say we have a 300, a 350 here. Right? Say we have a 350 here. If we have a 350, then the 350 will be different from 5250. And when 360 coming in, we have to go for 350, which means the DP has to follow this trajectory as well, right? So the DP is going to be the same. So the DP is going to be, that's for 0, 0, that's 2, that's 3, that's 4, that's 5, but 5 we have 3 level, and 6 we have 2 levels, and 7 we have 1 level, right? So that's the DP, and the index will be the same as the index in keys. So we go through keys, right? So this is how the DP is going to change. We're going to try to change the DP here. So we're now at 2, and then we're going to look 1 back, right? We're going to look 1 back, and then we say this is I, so look for I minus 1, and then within I minus 1, we'll use binary search to find the element that's just smaller than me, so it becomes 0. So we go look for 0, which contains 0. So I am going to add 1. So this one is going to be 1. So that's 3. And yeah, we have to go through every one of them. And then because that's just 1, so that's done. Now we're going to look for 3. So for 3, right, the key is 3. So we look at the first one is 200. So we go to 2, right, go 1. Before me, and we find if there's anything that's smaller. We find there's something smaller, and we look into its value. Its value is 1, so I'm going to add 1, so this one will be 2. And then I'm done. Now I'm going to go for 4, right? Now we're going to go for, the key is 4, which is here. We're going to look 1 ahead of me, and for 4 is 300, 1 ahead of me. We get this binary search. We find it's 200, which is smaller, which does have something smaller than me. So we binary search, we find the one that's just smaller than me, and we look, it's a 2, so for 4 with the plus 1, that's going to be 3. Okay, now this is where interesting things happen. So here we're going to go to 5, right? And go to 5, so we're going to go to 4 first. Right, so we'll go to 4, and when we go to 4, we check binary search, and we find out that there's nothing there. So we keep looking to 3, binary search, there is something there. So 5, the first one, will be, so this one will be 3, because 4 cannot afford, 3 can. And then if I want to go to the next one, again, go 1 level up to 4, and this one can afford, so this one becomes 4. And the last one, again, we go 1 previous, it can afford, so this one is 4 as well, right? Now we're going to go to 6. For 6, go to 5, and find 250, which is our target, so this one becomes 4. And next one, 370, coming in, go to 250 again. So this one is 4 as well. Then we're done. And finally, go for 7. 7 has to go 1 before. We'll go to 360. No, it's actually go to 370 because we want to find the one that's closest to you, right? So we go to 370, and 370 give us 4. So I have the last one is actually have to be this. This one is, oh man, that's not what I want to do. This one has to be like a list of lists as well. And the last one, right? Yeah. And it doesn't matter because it's not when we're going to code. But this one will be 4 plus 1 will be 5. And what do we return? We're going to return the maximum among these values, right? Maximum among these values. But most likely the maximum, because we're sorted, so the maximum will always be the last one because that's the biggest. Okay, let's try to code this idea. I don't think it's not trivial to set this up. So we're gonna say that's gonna be our DP. No, that's not DP. That's just env. Env dict gonna be a default dict. So we're gonna try to get from collections import default. Right, we're gonna go default dict. So there's gonna be a default dict, gonna be a list. And what we're gonna do is loop through everything, which is gonna say for with height in envelopes, and then we say inv dict with dot append height, right? And after we've done it, we're gonna say for v in inv for heights. We're gonna call it hs in env dict dot values, and we just say hs dot sort, right? I'm gonna sort it. Okay, now we're gonna say keys widths equals sorted, right? We're gonna sort again another thing, which is env dot keys, right? We're gonna sort it, and we're gonna also append. Oh, let's put a 0 here. Yeah, let's put a 0 here. So it's going to be env dict 0, gonna be append 0. So that's our like dummy value. So now we have everything. All right, we have everything. Now we're gonna say for I in range 1 to len ws, right? Oh, we also need what do we need? We need a DP as well. So we need have how do we do the DP? We can do hi. Can we just like swap? Yeah, we do DP on this directly because after we finish constructing this, we don't need, no, you need it. You definitely need it. And we need to create another DP just like the same as the env, like same as this, right? How do we create a DP the same as this, like in an easier way? I mean, we can just do, I don't know, man. We can envelope.length is 5,000. I mean, if you're talking about, I mean, we can just do like 5,000, right? We can do a 5,000 by 5,000. No, that's, yeah, let's set up a, let's do DP as well. So DP is going to be a dict. It's going to be a dictionary, right? And it's going to be the key. We actually don't need a key for. The key is going to be. Key is going to be the index, because that's how we are going to iterate. So the key is going to be index, right? key is going to be index, and the value is going to be 0 times something len h heights for what? For I in range. For I in range len ws. And where did you get hs? Hs going to be get by calling inf dict I wsi, right? So this is our DP. Now we have the DP, and we also need binary search. So from bisect import. So what type of do we want? We want if the find is the same if I insert in the left position. If I insert, if we find the same and we say we replace it, we're inserting to the left, and then we can look to the left. Yeah, I think should be bisect left. Okay, so we have the DP. Now we're gonna do. So it's going to be like this. If why did you delete it? We still need this. So we're gonna go I minus 1, right? We're gonna go I minus 1. So we're gonna say the current for I gonna be also for j in for j height in enumerate inf dict. Why did you do that? Because I want to go for I minus 1. But you can also do enumerate. I think enumerate will also be easier. So we're going to be with, yeah, I don't understand. Enumerate ws1, right? It's actually, what's enumerate? I remember enumerate can define which letter you want to go with. Where's enumerate? Here's enumerate. We can do start. So enumerate when I call start equals 1 because I want to skip 0, right? So this we can just call w, right? It'll be easier. So we call w here, which this one gives us every single height. Then what we do is we're gonna look for and in the previous. Hold on. Would that be like an even better way to do this? Like a 2 levels. So we are now restricting on the width. What if we have a width? And what if we also have a, we're gonna have a thing based on, I don't know, just like we have also 0 and 0, right? What if we have like a 100? It's a height. Height, we have 2, right? 200 is 3. 300 is 4. And we have actually 250 here is 5. Right? Then we have 360. That is 6. 370. That is also 6. Right? And then we have 380. That is 380. That is 7. And now we have 400. 400 is 5. and finally 500 is also 5. So what if we do like this, right? So we iterate on this first, and we find 0, so we're at 2, right? And then we say at 2, so the current we're looking at is 2, 100. So to 100, we need to look for something that's smaller than 2, right? We need to look for something that's smaller than 2, and then also if it does not exist, or if we look for something that's smaller than 100. Now let's do let's say here we're at 5, right? We are at 5 and we have a 250. So if we do 250, we look for the previous one is going to be 200, and 200 give us options is 3, and right, and if we look at 5 gives us option is 4. Five gives option 4, but this one doesn't work. Okay, so I don't think this is very systematic. Let's just finish off on this one. All right, so we have this. We enumerate. So we have a height. We have a width. Right. Now we want to go for k in range from I minus 1 to 0, right? And we're going to do binary search. So bisect left, it's going to be infdict what? Infdict, can I not do it as an infdict? I feel like it's just very convoluted, like really convoluted. What if I just, no, because the easiest way is because they are sorted, that's why. Okay, that's fine. Let's see, WSK, right? So when it's this H, we say index is this, right? And then we say if it's the same, we're gonna go, we just replace that position. And we're gonna see, right? It's gonna be insert into the right position, and we want something that's smaller than us. So we always check -1, the index -1. So we say if index -1 is larger than or equal to 0, which means exists, then what do we do? What we do is dp, let's also p potential pot h, the potential height equals, no, that's not potential height, that's potential width equals this, right? Then we're gonna call it pot w, so potential width, and then if this is correct, then we say dp, man, that is not what we want. Now we have we have a mixture of, geez, unbelievable. All right, we're gonna change the dp. We don't want this. We want it to be a width, and this is gonna be width. So just for width in WS, right? Way easier. So in that case, but we still need I because the widths are sorted, so it'll be easier for us to go back, right? To go backwards. So this has to be like this, and this has to be like this. This has to be like this, this has to be like this, but the DP can change because now DP we're using the width itself. So we say DP if it's successful, so DP width equals DP potential width plus 1. All right, and wouldn't break. Find the first one, wouldn't break, and it's just gonna keep looking. If we look through all of them and nothing, right? If it doesn't find anything, if it doesn't find anything, that's actually going to be 1, right? Because the base value is 1, so that's going to be 1, and then we're gonna also set DP 0 equals 0, right? DP 0 dot append 0, and we are not going to do. We're gonna do like that, like this. Can we actually? We can actually put this at the end, right? So here, WS does not contain 0. Then so we can avoid all this, and then this will be like the last push, right? We put 0 in it, and everybody's 1. So if it's good, and then we can enumerate. So we actually can enumerate everything, right? We're going to enumerate everything, and if a multiple, well, it's actually we don't have to because that's the smallest. Right? That's the smallest, so we can do this. Let's do this. That's fine. So we are skipping the first one. So we're skipping all the 2s, right? We go from 3s. We go from 3s, and we go from 3s. If you go from 3s, why do we even do this? Like, this is not even necessary, right? This is not necessary. We go from 3, right? We go from 3, and we look into all the height in the 3s. We go for anything that's smaller than I, which is 2, actually, and we look for it, and if we find it, we increment it. If we don't find it, don't do anything. Now, when we're done, we're going to return DP, right? WS minus 1 as the last, the biggest, right? This, and this one, we're going to return minus 1. So that's our thing, and we're going to try it. It's not correct. Can only concatenate. What is this? Yeah, so DPW is going to be a list. DPWJ, J equals DP potential, and then index minus 1. Okay, that one pass. Okay, so try these 2. They all pass. All right, let's try this. This is dynamic programming, and we are going to submit. Let's see, pending, judging. We got a wrong answer again. That's not the optimal. I think this definitely shall give us more correct answers than the previous one, right? I mean, we don't know, but I think so. I'm gonna take a look. And then last time, how many did we get? Like 30 something? That's still 30 something. Okay, so why is this thing wrong? Yep, this thing is wrong. Okay, don't panic. We're gonna figure it out. So we just print ws, print inf dict, right? Just to see if this one is correct. Okay, so I have 46, columns are 50, 50, and 52, 68. Yep. So, oh, I think maybe it's not the largest. Yeah, I think it's not the largest. Yeah, we don't have 3 at all. So 46 is 1, definitely. 50, we lock into 46, nothing happens. 52, we lock into 50, something happens, so this one becomes 2. And 72, we look into 52, nothing happens. We look into this, nothing happens. We look into this, nothing happens, so 72 is 1. 77, we look into this, that's 2. Oh, we look into this. You're not doing the maximum, man. You're not doing the maximum. That's why you're not doing the maximum. It has to be the maximum. So we do not break. Oh, dear God. We do not break. We do not break. We need to find the maximum. So as we do, this has to be the maximum, right? It's a maximum of dpwj and this. Then we pass. Which means we're gonna check every single one that's smaller than us, and we binary search into it, and we say, okay, this is the assumption that if we have, yes, I think this assumption is correct. Like if we have a width that's smaller than us, then the height that's closest to us but is smaller will contain the maximum. Right? So we kind of save another level of traverse here. Okay. This should be right, everybody. Oh my God, let's remove all this. Remove this. Yep. All right. Attempt number is number 4, right? No, I think it's number 3. Attempt number 3. Oh, I think we need those just in case. Okay, so try it. Pending. Judging. Ay, timeout. Jeez. Wow. Oh, but no worry, no worry. Timeout is not the. Oh, it's not timeout. I thought we time out. Wait, what's the? Oh, we got a 46. Ha. Okay. Okay. Okie dokie. All right. So this one give us 2, but we only return. I guess we just. I suspect this is not correct. I suspect we have to go through every single one of them. But that doesn't make any sense to me, man. It does not make any sense. All right, anyway. Confirm. Yeah, it's not correct. So what do? We are going to. Hi, why did you even delete it? We want to print everything. Okay, it's fine. We're gonna print it here. So I'm gonna print. Same thing, WS, I'm going to print DP, not DP, we're going to print in envelope dict, and we're going to print DP. All right, take a look. Okay, 1, 2, 6, 10. DP. Ah, it's not that, it's here. You're not looking at 10 because 10 only has 8. So 10 doesn't contain many of the stuff. Actually, 10 doesn't contain any of the stuff. So this is wrong. So we need to find the maximum. We don't even know where the maximum is. Oh, man. So we're going to do... what? What, rest is 0, right? For values, yeah, it's actually it's fine, for vals in dp.values. What happened if I just call max dp? I don't know. Return a max dp. Does this return what does it return? It return 10. So no. How about the values? What does this return? Actually, I don't know what that means. That's just no. Let's just like for vals in dp dot values, res equals max res max values, and then return res. Can we do this? I guess you can use reduce. Just saying. Think you can do reduce. You want to use reduce? From functools import reduce. I don't like reduce though, but make sure it pass. Yeah, that's the thing. Just in case we have to do it again. So let's say reduce function max and no, I think we'll probably have to do a lambda. It's the current and aggregate, right? Accumulate. And I'm going to say max accumulate and max accumulate. No. Max vals. Actually, we can do vals. And then this is going to be res and be res, right? I hope that I understand the syntax correct. I have not done this for a while, so I'm not quite sure. Let's see. Oh, list and int. What the heck? So every one of them when it gets out. Oh, that's fine. We can just do max, right? Yeah, max. No. How do we do this? So everything comes out, the values is going to be, but I want my result to be, okay, let's see Python reduce, but it's in functool, so I'm going to go for functools. Reduce, wait. Okay, function iterable. Okay, function iterable. So function is this. What's the signature of the function? Lambda. X is the accumulate. Oh, left is the accumulate. My bad. Left is the accumulate. So this is gonna be res. Right is the current. So left is the accumulate. Right is the current. If it is not given the first item, right? So we don't want the first item. We want to give an initializer. So we're going to say initializer initializer equals 0. Takes no keyword argument. Huh? How do you not take keyword argument? Isn't this a keyword argument? Is not? Did I spell it wrong? No. I don't know. How to do reduce with initializer. Accept all cookies. Oh, you just put it there. So it's not a keyword argument. It's just, you just put it there, I guess. There we go. There we go. That is correct. Okay, so we don't need this. We can use one line to represent this. And let's also change it to R, to VS, to save some keystrokes. Okay, I think this shall be right. I hope it doesn't time out. All right, let's hope it does not time out. Let's go. Pending. What is this? What is this? The runtime error. All right, I'll have so many submissions for this one. Pending judging. Come on, come on. Ew, I think this one is a real timeout then. Dang it. Timed out. TLE. Okay. Okay. I mean, we'd expect it's going to time out. Well, this means the algorithm, the idea is correct, but we just timed out. So these are all ON, right? These shall be fine. These shall be fine, right? And when we do enumerate here, we go for each width, and we look into we look at each width and look into each height of each width, and we try to find and we go one by one, right? We go to each one, and then we use binary search to find that even like with binary search in this one, it's still, I mean, because these two is actually ON, right? This part and this part is ON. And this part becomes ON squared. Because we have to go through each one of them. What if we don't go through each one of them? Can we not go through each one of them? But we won't know, right? Hold on, we actually do know. Like, do we really need to go through all of the Ks? I mean, we need to go through some Ks. Like in this case, I remember, if we don't go through all the Ks, then this test case will fail. Now it fails because I think it's from 77, right? It's 77. Yeah. And then I go for here, I just go for one of them, then because this one is not as big as this one. Well, that is because 81 will be fit for 68, right? Not 45. But we don't know, right? We have to check both. Like who is more limiting, right? So basically that's the question. So 52 is limiting, and 45 is also limiting. And the current strategy is we're gonna go check here, we get a value, go here, check, and go here, check. But we don't need to, right? That's the thing, because when we check here, this thing's already encompassing everything below. So how do we know that this is, the biggest so far? I mean, we don't know, right? We do not know. We do not know if this is the biggest so far. We go here, that's no good. No, that's good, but we want to keep going. And this is good. And we keep going. Like, when do we know we should stop iterating? Well, we know that we should stop iterating because this is the largest. I mean, every one is the largest. And if we hit here, right, and then if we keep going, if there's something that's bigger than this, then we need to investigate. But if everything is going to be smaller than this, that's like another check, right? It's another check. How do we check for it? So we already binary search to locate this, right? And now we have to go through all these. Do we need to go through all these? I mean, we know that this, right, cannot contain this because this one is smaller than this one. So this cannot contain this, which means this is at the same level as this one. And in fact, this one, because yeah, that's the limiting factor. So what should I do? Should I go for like when I see 250, right? Now we go looking for 200 and to find someone that's fit. So we're gonna find for this 203 for this, or we can go find because we tried 4, right? We tried ahead. So 5, we can try 4, right? So we say we are at 5, like this. So we're gonna try to find the one that's smaller, right? So we find 4, right? And within 4, and nothing fits, right? Or something will fit. So we find the first one that does fit, and then we go here and find something that does fit. So we go like 2 routes. One is based on height, the other is based on width. And each one we're gonna stop when we find the first one that does fit. Yeah, if you think about it, all we need is to find the first one that fits, either based on the criteria of the width or based on the criteria of the height. So in this case, right, for this case, 77, 81. So we want to find the first one, like the largest in terms of width that fits me, which gives us 7245. Then I want to find one that's the first one that fits me based on my height, which is 5268. Then we take the larger of these two. Because anything that's smaller, right, if it's smaller than 72 on the width, Uh, yeah, if anything that's smaller, say in terms of 72, right? If it has a smaller than 72, right? And then this is 45. Yeah, and then because this is also the largest, right? This is the largest that start with 72, right? The largest. So if there's anything that's smaller than 72 and with a width is also smaller than 45, then I'm covered by this already. The only thing that's not covered is if the height is larger than 45, which means that can be handled by looking for a height, the next height, which gives us 68. And the 5268 is the same thing if something that's smaller. Yeah, so we don't have to do max here. I want to leave this solution because we worked really hard to get to this solution. But we are going to change. So what we're saying is we're going to do 2 rounds of binary search, right? 2 rounds of binary search. The first round, we're going to search for, so first round will be based on, it's not really a binary search, right? It's not really a binary search. It is, so we have two dictionaries, right? And each dictionaries represent the width and the height. Now we're given a width and height, and then we go look in the dictionary, in the 2 dictionaries, and we try to find, like if, say for 5 and 250, right? We go 1 step back, and when you try to see on 4, and then we say there's nothing. Then we keep going again, so we find 3, 200, boom, we got it. So that's based on 5. And now we're going to also base on 250, right? So 250, we can go up, so that's 200, and we look for also binary search something that is just smaller than me, and boom, we find 203. So, and then my result will be the maximum of these 2, and that will be not going all the way back. Okay, so we're gonna do 2 dictionaries, right? So one dictionary, we call it a height dictionary, and we do another dictionary, we're gonna call it the width dictionary. So for this, it's gonna be this, so this is gonna be height dictionary, and this is gonna be width. No, we just call it height, width height, and this is height width, so it's a key value. So it's gonna be key value and key value. Key is H, value is W, right? And then we're gonna say this. That's gonna be key value. Is gonna be height, so we're gonna be WH, and we're gonna do another one here for this is gonna be W width. So this is gonna be height width, right? And then we're gonna have W's gonna be WH, and I'm gonna do height. It's gonna be height width. All right, so that's our preparation. And DP. What about DP? Honestly, deep. What about DP? No. DP is going to be doesn't matter. I think DP doesn't matter because I can just do I can do this. It's fine. Right? DP is fine. We say DP is just based on width. But do you know which one? Like I can pick width and height. width and height. So I need like a system I can cross-reference width and height, right? So it's going to just be a width and height. Yeah, just going to be width and height. 5,000 by 5,000. I think it's fine. I'm not sure like what's about the overhead and stuff, but I guess it's fine. So, because the length is only, oh, but it's 10,000. It's 10,000 on the total, so that might not be a right idea. So let's just do width, right? And oh, man. How about using tuples? All right, how about just using tuples? Let's try. Let's just use tuples, right? Let's just use tuples, and we just say for going to be this going to be 1 width and height for width height in envelopes, right? We just use tuples for this because all we need to do is to find the width and find the height. And now we're going to start. So what we're going to say is look for the height. Look for the search based on width, right? So we're going to say, oh, it's actually, I'm going to sort the envelopes and then go through the envelopes. Now we have the height and then we have the weight, right? We have the width and we have the height. But hold on, it's possible. Like even if you set up this way, it's possible that if we search like based on this, like 2 and a 100, if this one's really huge, 100 is really big, then it's not going to be, it might not be hit already, right? It might not hit already. So if we start from 0, start from 2 and a 100, what if we have like 2 and 1,000 here, right? 2 and 1,000, and we, not like 1,000, let's say 2 and 300, right? 2 and 300, and 2 give us nothing, and 300 should give us all these, and then we don't know any of these yet, right? We don't know all these yet. This seems to be not a viable solution either. I'm going to draw something, so bear with me right now. So we have 2 100, 3 200. No, actually I don't like this example. Now let's just use this example. We have, so they can connect 4 300. So they can connect and they can connect. And this will be this, right? And 5, I'll have 5 250. 5 250, 2 can connect, 3 can connect, 4 cannot connect. Now we have 5 400. 5 400. Now 2 can connect, 4 can connect, and also 3 can connect. Now 5 500. Same thing. 3 can connect, 2 can connect, 4 can connect. Now we have 6, 360. Only this can connect. This can, and everybody else can connect. So these two can connect. This can connect. This can connect. This can connect. This can connect. Right, 1, 2, 3. 1, 2. Hold on. No. It's not like that. It's not like, if you want to try to see like how many steps it's gonna take. Hold on, let's draw it again. So 2, 100. That's our starting point. And then we have 3, 200, right? And we say we can directly connect. So now, if I can contain you, so now 3, 200 is the starting point. Now I have 4, 300, and then we can connect. So theoretically 4, 300. Now it's 5, 200. I cannot connect this, but I can connect the pieces ahead of me, right? So we say 250. I would say 3, 200 can connect, right? And now we have another one. We say it's 5, 400. Now 5, 400. We'll level up. I can connect. And then 5, 500. We'll level up. I can connect. Now we have 6, 360. Look, level up. Can connect. And then these two cannot connect. And now 6, 370. Look up. Okay, connect here. And finally 7, 380. We look up. We can connect. And then we can connect. And then we just need to find the maximum steps going from like to 100. 1, 2, 3, 4, 5. What is like the longest path? I'm trying to turn this into a graph. See if I can find any intuition from graph. Or maybe we can. Like if the ones can completely contain in me, then like the maximum path, the longest path. And how do we construct this graph? Isn't the construction part is also going to take O(n) squared, right? Because for each, so because I'm going backwards, right? I'm going backwards, and have to check every single one of them. And if we create a link, if we check every single one of them, and then we create a link, man, I got stuck here.
Oh.
yeah, this is the requirement here. I mean, I was thinking like breaking it out into two, but then I realized if I break out into two, then the DP has no structure. Like I don't know which structure to follow. It's like it's not gonna work, right? If now I think the graph. I don't know about the graph. I think the graph, the construction of the graph would take O(n) squared time. Because basically I'm searching, right? When I do this, I'm searching. Like if I can find the graph, then I don't have. If I can construct the graph, then I already know the answer. Because that's basically doing this. I have to go through every one of them because yeah, because it could be. It's like this, right? I know the maximum for each node. I know the maximum of all the nodes ahead of me in a sorted order, right? I know the maximum of everything that's ahead of me. Now, how do I know the maximum for me? We can just go ahead, search everything ahead of us, and try to find the maximum. Right? We go here, we go every single thing. But the thing is, we don't have to search every single one because once we hit one that incorporates everything, then we can just stop here. We don't have to go. Incorporates everything. So shouldn't we have another flag, right? So we need to look ahead of before, right? We need to look backwards, and when we look backwards, we check if it's like if I can fit. If I can fit, I do it, and then I check if there's a flag. Now, if I have a flag that says I am currently the biggest, right? I'm currently the biggest, then I don't have to keep going. I go here and I'm done. If this one, like I'm not the currently biggest, so I have to keep going until I find the currently biggest. So this is the currently biggest. It contains everything. Let's try that idea. I mean, implementing wise, this one will be easier to implement. We just throw everything and throw everything on the wall and see which one stuck. Right? We still use our same idea as before, and then dp is going to be 1 times len envelopes. Right? Actually, as you say it, I think this has to be if you want a tuple, right? Because I want a flag, which is like currently is unknown, right? We don't know, and then we just say this for in range. No, in range. Right. So this is our DP, and let me say DP 0. That's our first one, and 1 gonna be true because this is the very first one is, you know, it contains everything, right? So we're gonna say for I and width and height in enumerate envelopes 1 and start equals 1, right? So for that, what we're gonna do is we're going to look backwards, right? We're going to look backwards and find the first one that has this flag set to 1. Like it's set to 1 when it is the biggest, right? How do I know that I'm the big? Like for this one, I know I'm not the biggest because the one before me is bigger than me, right? So for this one, so this is also not. But this one is not bigger. No, it doesn't work because this is bigger than this, right? But it is not bigger than this because this, the flag, is not set, right? This, I set this flag, say I'm the biggest, and then for here, I am now the biggest, so this one does not have the flag is not set. And then coming here, I do this, the flag is not set, so I keep going, and then this one is no good. So this one, the flag is not set. But we can jump, right? So I say, like if you reach me, I'm telling you that you don't have to hit this one, right? Because this one is, but like, how many do we jump? Like we can skip this one. But what if we have like 50, like different values in the height? If I have different values in the height, and they will all be sorted, right? They will all be sorted. Then, oh man. Oh. So they are all the maximum, right? And these positions, I say they are all the maximum. And I'm here. And I look backwards and I say, okay, I get you. Now what? Now I look backward again because I don't know if they will have a bigger than you, right? And then I just keep looking backwards. Yeah, that's 5,000 by 5,000. That's going to time out. I want to try to see if it times out. I think it's going to time out. All right, I'm just curious. dp equals 1 times len envelopes for I in range 1 to len envelopes, right? For j in range I minus 1, minus 1, minus 1. If envelopes I 0 larger than envelopes j, 0 and envelopes I1 larger than envelopes j1. Then we do dp I equals max dpi dp j plus 1. And then we return dp and return max dp. No position argument. Oh, I forgot a key. Yeah, I mean this will pass, but this is going to time out. So basically, but this will be like oh shoot, I forgot I said the solution too. This is runtime error. this is going to time out too. Although it doesn't have as much overhead. Yeah, it's going to time out. So we just, this one, I just want to make sure that it does time out. So the difficulty is how to make this one not time out. Yeah, it does time out. Did we time out at the same position? I think we actually progress more than our previous one. It does time out. So I have to make the DP smaller, which means that we cannot check every single one of them, right? So that is the thing. We cannot check every single one of them. So basically it's asking, when should we stop checking? When? Again, look at this, right? So this one's good. This I checked before, and it's no good. And this I checked. This is good, and do I have to check this one? I mean, you have to, right? But how do you know that this one is? I mean, you don't. Like going to this, I check this is bad. I check this is good. And what, we just stop? Like the first one that we can't, because if we check the first one, this one will be the first one, and then we know we have to keep checking. Oof. We know we have to keep checking, right? We cannot stop here. So basically, I want to find if there's any clue to tell me that I don't have to keep going, or like a clue to tell me where I shall be. That's why we, like, initially I list out all the length and all the width, but I'm not sure like how that can help us. I mean, we definitely don't need to keep checking, because like if you keep checking here, you know that this one is not going to fit. So like 81, we will know the fit will be 68, right? So we need to find a node that with 68. And 77, we need to find a node that's 72. And if they do not exist, if they do exist in the same node, then I do think that node is the best node. But if they do not exist in the same node, right? If they do not exist in the same node, then what do? Then we need to find the node that contains 72, okay, and the node that contains 68. And then we look through all of them and find the maximum in them. So now what I'm saying is we don't have to check anything that's smaller than 72, because if this is smaller than 72, and we already check everything starting with 72, yeah, we check everything that starts with 72. We check all of them, and we get a max, right, from all starting from 72. And anything that's smaller than 72 or 71, they will, like if they're smaller than 71, and then if the max on the height is also smaller, then they will not be bigger than this. And the same with here. So will this work. I think this is what we actually eventually trying to do later on, right? And then we kind of discarded this idea because we cannot find a good like DP to do it. Which means what we need is like what? Like 2 DP tables. One DP table will be based on weight. Hold on. What are we talking about here? Right? What we're talking about here is we need one DP table, which is based on, and how do you sync the 2 DP tables? I mean, you cannot sync like 77, I want to go 72, right? So everything starts at 72. So that is a DP table that will, with key is 72, and a value with shall be everything that's associated with 45, right? Or everything with every height, right? With every height. That's one DP table. And we need another one, which is 81, that will go with all of these. So that's 81. We're going to look into, so we find 68. So we need a height 68. So we'll be every envelope with height 68. And then we need to iterate through all of them. And then when we iterate through all of them, we will find like the maximum. So, okay, so we find the maximum based on this. So we have 2 DP tables. And after I find everything, and we're going to update. How do we update? Well, we're going to update both DP tables. So we just update it twice. This might work. Okay, so this is a wild idea. We have 2 TLE. This is the third one. We'll come back to the old idea. Like we're going to just do 2 rounds, right? We're doing 2 rounds. So we're going to build a two DP table. So we're going to say DP width is going to be, what is it going to be? It's going to be and we don't really care, right? We don't really care. Do we care? We don't care. So we're gonna be just like, so we say DP width and DP height. So one is based on height, the other is based on weight, based on width. And I'm gonna say for width and height in envelopes, right? And then we can do, it's not gonna be a default dict. It's going to be a default dict. A default dict inside is another dictionary, and that dictionary, yeah, so it's gonna be a default dict, and inside it's another dictionary, and this is also going to be a default dict. Inside is another dictionary. So we're gonna say dp w h equals 1, and do the same thing, but we just swap dph equals 1. All right, so that's the setup. Now we're gonna sort it. So we create these and then we sort it. Okay, so envelopes is sorted, and WS gonna be if I sort it first, then I don't have to sort again because the W's will be sorted. and the H will be sorted as well. No, H will not be sorted overall. So we do have to do, yeah, so it has to be sorted, dpw dot sorted dpw dot keys, right? And heights will be sorted dph dot keys. All right. Now we are ready, so we're gonna go starting from the second, right? Same thing as before. We're starting from the second. So we're starting from the second. We don't have to do the W, right? We don't have to do the W. Do we have to do the W? Now, because we are iterating through every single envelope, right? We're doing every single envelope. And if we're doing every single envelope, what we need is do need a binary search for this because there might be repeats, right? So we cannot just say it's going to one before. No, so we're going to do index, going to be index, not index, yeah, it's index. Index width equals bisect left. I'm going to say width, and currently WH equals envelopes I, right? And this is going to be width, and we also do, so now we're based on width. So we find the index of width, and it's going to be left. So I'm going to say it's going to be index width minus 1, right? If minus 1 is smaller than 0, then we don't even consider it because this could be nothing will be smaller than you. So I'm going to say if index width minus 1 is larger than or equal to 0, we actually have to do while. While this is larger than or equal to 0, then while it's larger or equal to 0, then we do it once, then we can break it, right? Then we say, what do we say? What do we say? We have to go inside and loop through everything. We have to loop through everything that's based on the width, right? That's based on the width. Like loop through everything based on the width. But if nothing is bigger, then we have to go one back, right? So we say what do we say? We say in a DPW, potential heights equals potential heights equals dpw index is larger than 0, so potential width is equal to ws index this. So this is going to be potential width, and in this width we have all the heights. So it's dot keys. That's the potential heights, and we're going to run another binary search, right? Another binary search. We say oh man, index W, and then this can be IH equals binary search left, potential, well, but it's not sorted. It's not sorted. No, let's just go through the entire thing. I don't think it will cost too much. Right? Would it cost too much? Oh, Lord. Oh, God help me. So we're gonna say if max potential this is larger, no, yes, wait, the mean. If the smallest of the potential heights is larger than me, right, then we continue. But if it's smaller or equal to me, then we iterate through everything. Let's just go through everything. It's fine. No, I don't really have to care anymore. Or we just go through everything because we can't mean we already go through everything. Anyway, if it's smaller than h, then we're gonna say for potential h in potential hs, right? For potential this in potential this, dp w. So we currently based on w, so we say w and h equals max dp w in h, right? And dpw for this in this, if potential h is smaller than h, actually it has to be smaller. Mean is if the mean is, yeah, it has to be smaller, because if the mean is equal, then it's no good. So if it's this, then equals this, potential w, potential h plus 1, right? So that's we go through all the potential h, and you do need a flag. You do need a flag, so we just go through everything. Right, we're gonna say updated equals false, right? And then we go through everything. If this happens, then we say updated equals true, right? And once we exit, we say if updated, then we break. We don't have to keep going. If not updated, which means every one of them is larger or equal to h, then what we need to do is the index w has to minus. We go to the next one, previous one. So that is based on w. So we can do exactly the same thing, right? Exactly the same thing. And then we can say this is based on width, and this will be based on height. So this is going to be h, this is going to be h, this is going to be h, right? And while this equals 0, so potential h equals hsh, and then potential weights equals height and height, right? And then we say potential weight and potential weights. If the potential weight is smaller than my current weight, then IM equal to maximum IM, and this is just going to be potential height, and potential weight. Update is true. If not true, and then we're in a decrement H. And and this is actually not right. This is W. This has to be H. H, W. This is also H, H, W. Right. So now, based on the two, I have a potential. I have dpHW and dpWH. Right. We have two values. Now, I'm going to say the I'm also going to have a res here equals 0, so it goes through every single one of them. And then I'm going to say res equals max dpw wh and dph hw. And after we get this, dpw wh can be res, and the dph hw is going to be res as well, because they have to be synchronized, right? They have to be synchronized. So now we just go through every single one of them. That's ON. And in here, we won't, as long as we can find something, and then we just break. Okay, so we have to return, right? When the return, after go through everything, we say return res. All right, let's take a look at 3. Ugh, I didn't even pass the last one. Of course we don't pass the last one, because this is not res. This is not res. That's not right. This and this will equal to this. No. We have to return the maximum of the dp. All right, so we're going to say for the value is a dictionary itself. My lord. The value is a dictionary itself. So can be, let's just say for vowels in dpw, right? So dpw, the values is another dictionary. So I actually call dicts in this, and then for dicts in this, and then for values, for vowels in dicts, right? What we're gonna do is we're gonna do max vowels, right? And then I'm gonna say max this. Okay, that is not correct. Generator is not working. For dicts in this, and then for vowels in dicts, dot. Well, for each, so I shouldn't say for, it's a DIC, I just call it DIC dictionary, right? Values, right? Nope, it's still not right. Oh, because here, dot values, still not right. Oh, Lord. Okay, so what are we doing? So we want to iterate through all the values, and then within all the values, we want to get the value, and then when we get the value, we want to take the maximum of this value. And we take the maximum of the max. But it says max integer is not iterable. Oh, this is integer. No, integer. Alright, let's not do it this way. Let's just go res is 0, right? When you just say for dic in this, and then for vowels in this, res equals max, res, and the max vowels, and then return res. Alright, I think just understanding of my DP structure. Hold on. What's dpw.values? dpw.values is dictionaries, right? It's a list of dictionaries. And then we say for each dictionaries init. Now for each dictionaries init, I can call dictionary.values, which gives me so each dictionary value should give me a list. Oh, I can already call max here. That's why it's max gonna be here. Yeah. I just confused. It's going to be like this, right? And then return res. Okay. This I think I can write max. Max what? Max dic.values for dic in dpw.values. Built-in function is not iterable because I forgot the parentheses. Okay, I'm not so sure about this. What is it used? If this one still doesn't work, I'm going to check the results. Check the answer. I think this is my last hope. It's wildly complicated. I'll just run it. I've never run this one and see how long it's taken. Kind of just gauge if it's possible. Ugh, the answer is wrong. Jeez, the answer is wrong. We have a wrong answer. No way, have wrong answer. God. So like this idea doesn't even work. Oh, this is take forever. Yeah, but it does give the right answer. This one gives the wrong answer. So what did I? It's been 2 hours. I think I'm going to give up. I don't know. I thought this was gonna work based on width. I work on all these. It doesn't work on that one. Man, why would it not work? Which means if it does not work, that means the maximum does not happen, which if you think about it, does make sense. No, it doesn't make sense. Why would it not happen here? Why would it not happen? I don't know. It just says it does not happen. I seriously don't want to give up. I think it's still possible. I just don't understand. Like, how is this not correct? All right, we run the code. This one gives us my answer is 33. Jeez. I don't know. Let's see. Oh my god, there's a lot of numbers. Let's from the start. We'll pick a random end. Just kind of see if this one pass. Trying to find a small. Oh, this one does not pass. That's small enough. Okay, that one pass. Let's pick a slightly bigger one. This one does not pass. Which just means that if we get here and like if we update it, right? And I think that we have a maximum, which actually is not. I already iterated through everything, right? Everything in a potential W, and you update it as it's true, which means I have to keep going, right? Keep going. Is that what it means? Okay, let's do this, right? Let's say we comment out these and then run the code. This shall be correct. Yes, which means, which basically means we have to keep going. Like, if we do one, that's not enough. But how? How? Just like I have something even smaller, right? I have something smaller in either width or height. But it can incorporate more. But the hope is by doing it on both ends, we can avoid this from happening. Anyway, let's get rid of this and try again. Try to see if we can find a minimum example. Okay, so we're still on good luck. Try again here. Okay, that's still good. I'm gonna try another one. Still good. That's good. Try another one. We're still good, but we're getting closer. Try another one. No, this one's good, so we can control C. So let's just try the two of these and try it. Oh, yeah, they also work. So just one of these. Okay, so I mean it's not too bad. It's not too bad. We can handle this, right? Yeah, I think we can handle this. It's not too long. Okay, it's all right. So the answer is 7, but we only get 6. And to prevent from screaming, oh, we're getting into 3 hours. Okay. All right, let's take a look. Just want to print the envelope for now. Yeah, it's still too long. DPW. We have 6s here. Man, this is hard to analyze. It's just so, I can't analyze this. This is still too much. Anyway, let's see if we can reduce from the front. Maybe we can, let's say, reduce here, but we still get, yep, okay. Yeah, no, so I can reduce 1. I'll just try delete something in the middle. Nope. How about here? Oh. Nope. So I think we tried every single one. Let's just do one at a time then. Oh, that's not good. I don't know. I just randomly pick some values to remove. A lot of them are important. Try this one. Okay, this one's good. There's no reason to try this one, but we'll just try it again. Okay, that's also good. Let's try it again. Nope, this one's no good. Try the one in the next one. That's not good. What else can we delete? Let's try the first one. See if that one can work. Yep, that one works. So keep trying. It's random, pick one, see it. No, this one doesn't work. How about this one? Yep, this one works. And how about this one? Too fast. This one works. How about this one again? Nope, doesn't work. Yeah, I'm just basically removing every single one. See if when will we get down to nice. This is like 10, I think. Now it's probably manageable. Yeah, nice. Keep getting down. It probably will do even longer time. How about this one? This one works as well. Okay. So we have reduced it significantly in size. No, this one does not work. Okay. I think we'll try this one. Let's try that. We should have do a systematic chain. Now I don't know which one I have tried, which one I have not tried. It's pretty stupid of me. And oh, this one works. How about this one? Now we have 9. If this one works, then we can try to work on this one. 10. It's doable. 10 I think is doable. Yeah, 10 I think is. Wait, what's the answer for this one? Is that 5? 6. 5. It's 5. Yeah, this I think is manageable. Yeah, this becomes manageable. So we can even fit in one line. Okay, so this is the start, right? And this one's 1, and then this cannot fit. So basically we try to find a thing smaller than 3275, and then nothing is smaller than 3275. We can actually print dp height as well. So we have 2, right? And then we have yeah, that's nothing there. It's actually fine. Let's just do 1. It's too much clutter. Now, this, when we look for, okay, we can actually do. Let's do this. I'm gonna print ws and print hs. Alright, the ws hs. So w, actually I don't need to print ws because I know ws by this. This is hs, right? So we know this is 1. So we're starting from here, right? We're starting from here. And ws tell me I need to look in this, right? But looking here, this is smaller than 1, so we don't do anything. And now we're looking to hs. hs 32, we need to look into 792. So 792 give us this, right? 792 give us this, and then it doesn't fit, so this will be 1 as well. Now, so here, 3260. 3260, we need to find this. So good, 3260 on the W side, we get 2. And this is 32, yeah, we get 2. And then on 49, this, we need to get 3275, which is also here, which is also 2, which gives us 2. So this one's 2, that's good. Keep going. So here, 3676, we're looking for here. So that's give us 2. 7605. 7605 will give us 6469. Where is 6469? 6469 is here. So this will give us 1. Then for this 76, this one will give us 3. Yes, 3. I was going to say 2, but it is 3 because this one is 2. 3260. This one is 2. So this one is 3. Okay, good. That's 3. Now 4154. 4154. We're gonna go for here, and doesn't work. Right? Doesn't work. So 414. This one would be 1. And 792 doesn't work. So 4154 is 1. Yep. 4660. We're looking in here, and that's 1. I think that's what the problem is. We can actually get into here, right? Because this is bad. But we shall be able to get somewhere here. Oh, this will get us 7730. 7730 is here. which get us 1728. So this becomes 2. But in fact, I can incorporate this, which shall give us, it shall give us 4. This shall give us 4. So like this shall give us 4. And then come here, going 1 back, that shall give us 5, right? Yeah, here's where we get 5 from. That's the 5. That's the 5. But now we can't. Like, they just mismatch. Like this one we match into here, which is bad. And then this one we match into here, which is also bad. So both are bad. So yeah, this does not work. Okay, it does not work. But if we iterate backwards, yeah, it's not like how do we know that this is bad? Like how do we know which one is good so that I can use? I mean, we can iterate, like say a few, but we cannot go all the way back, right? So like we iterate this one, and it's a bad one, right? It's not a bad one. It fits. 792 fits, but we know that it's just, it's just doesn't feel right. You have to keep looking before. Now, how do we know which one we shall stop? Like we need to stop here, because we don't need to go here, because this one gives this one, right? So if we iterate this one say has no previous, the previous is 0, and okay, and we keep going, and this one say previous is this one, so we don't need to go here because we already did it, right? And that means we can skip to this -1. Actually, this one comes from here. So if I inherit things here, so this will give me the first that I have incorporated, which is this one, right? So this will give us the first envelope, the smallest envelope in my current collection, which means for me, you don't have to go through all of those, because if you go through any one in between, so do I just go to the one that's ahead of the smallest? Is that what you're saying? Like if like the idea is I need to skip, right? I need to skip. So if I go here, I can skip, right, to the front, and I go here and I say I skip. But like, why do I still keep going? Because this one contains nothing, right? And say this one contains 3, and this one contains only 1. And what I want is the maximum. So I go here and I think, why do you keep going, right? Why do you keep going? If you have the idea of skipping, now this, because it doesn't contain anything. So are we having a rule that if you don't contain anything, we're going to keep going? So we keep going to here. And this, I say, contains 3, which means there are 3 that we don't have to check. This contains 1. That means we have 0 that we don't have to check. We have to keep checking. This contains 2, right? This, we check this, so it has 2. So it means we don't have to check those 2. And we can actually have those 2 listed. So we don't check these 2. So we check
the ones that's not contained inside. Then you have to decide which one to check. Like when you go backwards, you have to decide which one to check. So like this one will tell us we have to check everything. This one tells us we don't have to check like this and this, but we still have to go all the way back, right? Like the ideal is if we can stop early. I mean, like for this, I say I contain 2, so I say I skip these 2, right? Because so, or like if here I have a list of nodes, a list indexes that I do not contain. So when we hit here, I just go to the ones that I do not contain. And every one will contain the one that they do not contain. So I just go for the ones that they do not contain. We prepare a set, right? So when we are here, we need to know which one that we need to visit. And we create a list, a set of everything. And we go here and we remove the ones that we don't need to visit. And then it's going to be a set. So everything will be a set. So we just do a set minus set. All right. And then we check if this one's in the set. Then we go here, remove everything from it. And then we see how many is still in the set. And then we go for the highest in the set. All right, we go the highest in the set, and then we remove the things that I do not need to check in the set. And then from there, I go to the highest in the set. And then from there, I remove. Will this make it faster? Oh man, I don't know. All right, this is going to be my last try. If it still doesn't work, I'm gonna call it quits. So this one's error, so I don't even need to keep this. I don't want to keep this. If this one's wrong. So what you're saying is, so we're gonna sort it, right? For sure. And our DP is going to be 1, right? 1 and something. Something's going to be a set, right? For this in range len envelopes, right? So this is our DP. And then we're going to say, so the same thing, right? So we're going to get WH, and then potential indices, right, equals set range I, right? That's my potential indices, is everything up until myself that I need to visit. Now we're gonna start visiting, and we say while potential indices, right? And current next I will equal to max potential indices. So we pick the maximum out, right? And then after it picks the maximum out, after it picked maximum out and then visit it, right? When I visit it, so we're gonna say we visited the DP next I, right? DP next I. So we're gonna say if, right? If the DP next I, it fits. What if it doesn't fit? If it doesn't fit, we just keep looking one in front of it, right? Until we find something that fits. Right. So we say if envelopes. Oh, I guess let's say ni. Okay, ni is this. So nwnh equals envelopes in I, right? Envelopes in I. And I'm going to say if nw is smaller than w and nh is smaller than h, so that one fits, then we do dp, right? dpi, right? dpi 0 equals max, dpi 0 and dp ni 0 plus 1. And we say do we how do you handle potential indexes if it's correct, right? So like here, I am at where am I? I'm here, and I go here. So what? Like, is that potentially you're gonna? Yes, it's gonna be like this. If this is larger than dp I0, right? Then we say what do we say? We say, how do you copy a set? Can you copy a set using a equals set 1, 2, 3, right? B equals a. Can I do this? No. A dot copy. I can do copy. B equals a dot copy. B a dot remove. 2 a b. Oh, I can do copy. Okay. No, that's wrong right here. So if is larger, so and take it. So we say dpi and dpi 0 equals dp ni 0 plus 1, and we're gonna say I can do union, right? So a dot union, because a dot add is add itself. A dot update 3. Nope. Has to be set 3, right? Has to be like this. Oh no, 2. Yeah, have to be updating this. No, it's still, I want a plus 4. No, a dot union 4. Okay, so I can call dot union for this. I got the wrong thing again. So where am I? I'm here. So if this is the case, so do I include? I mean, you should include yourself, right? So it's going to be, you're going to include yourself as the index, right? So it's going to be I. So you include yourself. So everyone is itself. So when you do this, and we say dpi 1 equals dpi 1 dot union dp ni 1, right? So this is when it works, and then that means we have visited it, right? We have visited. What if it's smaller? If it's smaller, then you don't do anything, right? Only after you have visited it, and then you're gonna remove it. So we say if it's good, and we try to see if it's smaller. If it is, then if it is larger than me, then I incorporate it. If it is not larger than me, then I don't incorporate you. I just skip. But every time, man, this is just decision whether I update or not, but every time I see something I could have incorporated, right? And then that means everything that one contains should also be eliminated. So we're gonna eliminate it. So we're gonna do this, right? And then potential indices, right? We can do, I think it's A, B, A minus B. Yeah, we can do A minus B. We can do a minus. So every time I visited in potential indices, we're gonna minus itself. Minus what? Minus dp ni 1. So this is like everything that it contains. So we're gonna minus it, right? So we're reducing potential indices to C. And after we remove it, coming back up, we're gonna try to find the potential indices again. And we get into it. If it's good, we update. It's not gonna be this union. It's going to be it's going to be what? I dot union. Because every single time you're gonna change. So it's gonna be I dot union something, right? I dot union something. Let's see what's gonna happen. Like 1 dot union set. This should be given us a 1. Yeah, this is fine. Right, so this one will always be like all the thing that's contained inside, and if it's good, then we'll always remove so we don't have to visit them anymore. And then coming back up, we check if it's not, we're gonna keep visiting, right? And until we finish, right? And finish, and then okay, then we finish, then we're gonna return maximum the v for v this in dp, right? So it's just the maximum. I think I can actually call maximum dp. No, let's just call it this way. Okay, let's try, see if this one works. Oh, I forgot something. So if this, right, else, can we like pop it? Does set has pop? I don't know. The set, no, it has remove. The set has pop. Actually, that's a good question. A dot pop. Wait, set dot pop. I think it's we have a. I think it just pop any pop 3. What's set dot pop? It's just like a random thing it gets popped out. Yeah, I'd rather call remove. So pop dot remove and I, right? Where? Oh, we don't have else because we already removed. We removed the ni. That will include itself. So remove, yeah, it will remove by itself. So we don't have to remove here. We do else, and then we say remove it. Okay. We pass in this one. All right, this is the last shot. If it doesn't work, then I am giving up. All right, this is the last shot. I'm going to use this just to gauge how long it takes or whether it's even accurate. Not sure. No, it's not working. It's not working. My God, I'm TLE on this one directly. Jeez. This isn't a TLE. All right, giving up. Let's see what's the solution for this one. Damn, this one's hard. Has 3 TLEs. It must be something built upon this, because this is the easiest way forward. This TLE, I thought it's a good idea, right? We remove all the potential indices, but it's not working because union and everything. I think just add a lot of overhead to it. All right, let's check. Yeah, look at the struggle. All right, let's see. And log in. Okay. Find the longest increasing subsequence based on height. Yes. 4, 3, 4 before. Longest increasing. Oh man, it rings a bell. It rings a bell. It rings a bell. Let's go back here. Go back to the basics. It rings a bell. So we have 2, 3, right? Just kind of think what that answer is saying. We have 2, 3, 5, 4, 6, 4, and 6, 7, right? That's how I sort it. And what I say is, I want to find, so what they say is, you need to find the longest increasing subsequence that's based on the heights, right? However, if you do it this way, yes, that's correct, because the width has been sorted already. So what you need to do is the longest increasing subsequence on height. Now, if we want to do longest on height, we cannot do this way because these are the same. So we will count 7, 4, and 7. We cannot count 4 and 7. What they say is we're going to change it. We do 7 and 4, which means we're going to reverse the order. Okay. So the longest increasing subsequence. So we do 3, 4, 7. That's good. And keep going. That's no good. What if we found something smaller? The longest so we're gonna sort it that way, right? Okay, so let's try this one, because that one is like already done. I kind of need some more example to help us understand. So these are sorted. So we have 89, 53, right? So we do 89, 53, that's only one. So 53, if it's larger than this, then we increment. If it's not larger than this, then we need to find, how do we find the largest, like ahead of you? We don't know. Right, we have here, so we decrease. So whenever we decrease, we reset. No, it's subsequence. Subsequence, we need to know the thing that's ahead of me. Isn't that, I go back to the same problem, right? 53, 68, and 45 is not good. And 81. So when we hit 81, how do we know that we're gonna go for 68? So we have to go like this way, right? So we'll go 45, and 45 is 1 because it's a decrease. But we don't know it's 1 because we have to know what is ahead of it. How do we do longest increasing subsequence? We have 89, 53. Are you telling me the stack? Oh, that might be stack. 89. Now 53 coming in. We're gonna pop everything that's bigger than me. Now 68 coming in. Now 45 coming in. I'm gonna pop things that's bigger than me. And now 81 coming in. That doesn't make any sense. Right, that doesn't make any sense. No, we shall pop. Hold on. We shall pop 45, right? So 45, so we're decreasing, and then if we find something bigger, and then we pop. No. How do we find the longest increasing subsequence? Isn't that 89, 53, 68, 45, and 81. We want to find the longest increasing subsequence, which is 53, 68,
and 81, right? This is the one we want. How do we look for it? If I say, if we use dp, right? So we say we're here, that's 1, and we're here, we say if it's, so we either, if the thing's in front of me is smaller than me, then we need that, and plus 1. If the thing in front of me is bigger than me, then I either start over or find the one that's smaller than me. Like for 45. And what do we do for 45? Or what do we do for 81? Right? For 81. And we say 45 is actually 1. 68 is 2. Now for 81, how do we know we need to go to 68 instead of stop at 45? I say I get here. Man, no, I don't know how to do that. I need to check again. How do you do the longest? Anyway, so this is a compare for sorting. Binary search. Oh. Oh. Binary search. No, that doesn't make any sense still. Binary search DP. What is DP? Zero LAN envelope 1. Envelope 1 is the width, and I see that we already sort the envelope. So envelope 1 is the width, and binary search, what, based on DP? What is DP? DP is always 0. 0 and LAN is 0. So up to now, from 0 to LAN, okay? From 0 to LAN, with binary search on DP, if index smaller than 0, which means don't find anything, index DP index equals okay, so our problem is when I hit 81, I don't know which one I need to go for, right? So what I do is I have 81 and I want to do a binary search on the DP. What is DP? I think DP is the longest increasing subsequence. I think that is DP. So if DP is the longest increasing subsequence, and I have 81 coming in, so I want to search inside DP to know where I can be, right? And if index is smaller than 0, I think that means it's it's outside, right? If index is smaller than 0, then it's outside. No. If index is smaller than 0, that means it's ahead, which means my current is the smallest. And if my current is the smallest, so I swap. But I don't know. Do I have this? Have you done this before? Don't quite understand this algorithm, to be honest with you. I kind of see that the DP is simply the longest increasing subsequence, right? The things we're trying to find. We say if index, it means the current one is the biggest one, so we add it. Yeah, the current one's the biggest one. What if the current one is not the biggest one? The current one is but how could you just do subsequence? You cannot change order. You can pick and choose, but you cannot change order. Let's say DP is larger than 0, and I just say DP index equals this. What is the longest increasing subsequence? Don't tell me I've done this before. I'll be very unhappy if I've done this before. Oh my goodness, I did do it before. I cannot figure out how this one is done. Alright, so that can be derived by deleting, okay. The longest increase subsequence is 2, 3, 7. I've done this before, but I forgot how I did it. Okay, index is binary search auxiliary if n is equal to index minus 1. I'm going to continue. What's that? What's n equals index minus 1? We do by right. Okay, and minus 1. So these two, this means the current is the same, just to handle repeated situations, the same. So I say I continue, yes, if this means I'm the biggest. Otherwise, auxiliary index equals n. How can I do this? Didn't I change the order? So yeah, binary search, and I find a position to insert my current value. But I'm going right. I'm going this way, and I find, say I have 10. That's the first one, and the next one is 9. And if I do binary search on 9, this will result in 0. And this one is not. This is not good. And then index is 0 is not. So we say auxiliary 0 equals 9. Okay, that's fine. So auxiliary will be 2. So this. How about 3? Huh? Oh. Oh, it is. Auxiliary is the current. But hold on. So 7. What if I have like 4? So like this is fine. So I get 2, and I swap 3, and then 7. What if I have 4? Well, I'll say 4 will swap out 7. which is the same. What if I swap out something in here? Yeah, what if I have a 4? Do we swap out 3? No, I will. Auxiliary index. What if, like, seriously, if an index is like somewhere in the front, but not the. What if the index is the first one? You just start over? I can't wrap my head around with this thing. No, I cannot. Index. If I'm currently the smallest, if I encounter a smallest value, right? I just say here I have a 1, right? I have a 1, and we have 2, 3 here. I have a 1, and then we do this search. The result will be 0, and if not, so we say auxiliary 0. So it becomes what, 3, 1? Doesn't make any sense, right? Like 1, 3. I guess it will be 1. I incorporate 1 in here. We swap out. But that's not the subsequence, right? Yeah, if it is 1, it should still be 2, 3. But we will give us 1, 3. Not brute force. Recursion with memorization. Dynamic programming. Binary search. We also make use of DP array with all 0. DP array is meant to store the increasing subsequence, okay? Counted element. While traversing the nums array, we keep on filling the DP array with the elements encountered so far. The element corresponding to the jth index determines correct position in the DP array by making use of binary search, okay? We also insert it at that correct position. And also insert. An important point to note is that for binary search, we consider only that position of the DP in which we have made the updates by the schematics at their correct position. Okay. Thus, only the elements up to the ith index in the DP array can determine the position of the current element in it. Since the element enters its correct position high in ascending order, the subsequent form so far in it is surely an increasing subsequence. Now this position index becomes equal to the length, and then we need to update the length. That's, yes, DP does not result in the longest increasing subsequence, but length of DP array will give you length of LIS. Not the longest, but the length of DP results in length of the longest. Why? Because it doesn't hurt. Basically, we're just swapping it out with, okay, so what it means is as you are traversing the original array, for each value, right, you have a DP is strictly increasing, right? DP is strictly increasing, and every time we encounter something smaller, something that's inside the DP array, you just swap it out because it doesn't hurt, right? Because it does not hurt. Because when we swap out, it's already in there.
So we swap out, and if we keep going on, I don't understand why it is the same length. Why is it the same length? It doesn't make any sense. So 0 for 12. That is the idea, but then we swap out. But why do we swap? I mean, do we have to swap it out? The swap out is just to put the current number in the position of an increasing, right? In the increasing array. If we don't have anything smaller. So which means when we swap, it's always reducing the size. Okay, let's see. Is this one the same idea? Maybe I can give us some the longest up to the ith index, given is independent of increments coming later on. Thus, if we know the length of LIS up to the ith index, we can figure out the length by including the I plus 1th element based on the elements with instance j. We make use of a DP array to store the required data, and it represents the length of the longest increasing possible, considering the array ends up necessarily including the ith. We need to try to append the current elements in every possible increasing subsequence up to such that the new subsequence formed by adding, that's an O(n) squared, right? Let's just see this. 1, 2. I will compare, and then it's larger, we don't change. Here is larger, we don't change. This will change to 2. 3. Yeah, this is like basic DP. Like we can do this. 7. And so this we updated 2. And then this updated 3. And then this we updated 3 to 2. Yeah, and then this one was 4. Yeah, this is like the basic DP solution, but we cannot use it because it's going to time out. Read it again. Store the increasing subsequence formed by including the currently encountered. That's not subsequence, right? It's just because you're swapping it. We're keeping on filling the DP array with the elements encountered so far. It determines correct position in the DP array by making use of binary search. And also insert at the correct position. I don't understand. Why do we insert in the correct position? Only that portion of the DP array in which we have made the updates by inserting some elements at their correct position. Thus, only the elements up to the ith index can determine the position of the current element in it. Okay, that is fine. Since the element enters its correct position in an ascending order, the subsequence formed so far and it is surely increasing. But that's not a subsequence because you are just inserting numbers into it. All right, let's take a look. Maybe I wrote something. Obtain a subsequence of increasing numbers. each new element x. If x is larger, yes, else find that's just larger than x. Replace that element with x. S is not the increasing subsequence looking for. However, the length is the correct answer. When we replace si with x, we don't change the length of answer, but we change the potential best candidate. The idea is to try to make each position as small as possible. The actual sequence only changes when we append a number. Otherwise, it's just a virtual change. We try to make each number small, so we'll have a larger chance to append more numbers. Okay, that seems to make sense to me. So what we traverse through, and for each value, we try to binary. So that's not a substitute. That's just the like say we only have one, right? And then every time we find, and then so let's say, okay, let's do it this way. Let's say the DP array currently is the increasing subsequence, right? And then we have a smaller value, right? We have a smaller value, and we want to replace, because anything we replace inside the DP array will not change its length. Its length will remain the same, right? The length will remain the same. And so that's fine. So the only time we increase is when, now it makes sense. The only time we increase the length is when we append it. And what we want is to have this array to be as small as possible for each value in it, to be as small as possible. But basically it's actually for the last one to be as small as possible, right? For the last one to be as small as possible. So as we go through, the ideal is as we go through, we're going to keep swapping. Like after you swap, it's not going to be true. But if the thing you swap is the last value, then that's what we want, right? That's what we want. So we just constantly swapping. If we do not append, right? If we do not append a new value, then it's uncertain whether the current DP array represents the longest increasing subsequence. But if we append a new value, then it makes everything correct. Actually, we don't even have to append. When we change the last value of the DP array, and that's when it makes everything legit, right? That means we do have a value. No, that's still not legit. No, that's still not legit because it could be, the value is encountered before, right? We have a value encountered before, and we have a small value encountered later, and we have a value we encounter now that we change the current last value, but the previous it's still swapped, right? The small value comes later. But it doesn't matter. The small value comes, it's swapping out one of the values in it that's slightly bigger, right? It doesn't really matter, because if we swap it back, we can always swap it back, right? We swap it just to make the DP array as small as possible to append new values. Because when we swap it, it doesn't change. We only change one value into it, right? When we change one value, we do not change the order. Like the order of the DP array remains the same. And it arrives here because it has appended something. Every time it append, and that's a real increase in the longest increasing array. So that does make sense, but it's still, I shall, if I encounter this one again, I will solve with a DP solution, but it's still, this is not going to be a solution that I'm going to come up with. Incrementally building the longest. I should put this, I should add this one, add to a list, into nightmare list. Probably it's already in the nightmare list. Yeah. All right, so now going back here, that makes more sense now. So it is a basic, it is a DP solution, right? So coming back here, we just, we sorted, and then we going one by one, and it's not gonna work. Now we just need to have this intuition. That is, we sort the same way, right? After we sort it, then we need to get the longest, the longest increasing subsequence on heights, right? On heights. Okay, so here it is, solution 4, which now I did not get. So we're gonna sort based on, yeah, this has to be minus, because we want a descending, because if it's ascending, then the longest subsequence on the heights will include all of them, because they're increasing, right? So we need to reverse them, so we make sure that with the same height, with the same width, the heights do not count. None of them will be included. So we sort here. Notice we sort ascending on width, but descending on height. Right, and then we say heights equals to H for H in envelopes. Right, now we just need to count how many, like the length of this. So we're gonna have a DP equals this. Right, we're gonna say for height in heights. Actually, we're gonna put HS0 into it, and this is gonna be 1. And we say index equals binary search. On the right instead of left. Right, when I search binary search to the right, DP. Actually, I can start from. I think it's fine. Yeah, I think it's fine. Just DP and then H, right? So this one will give us, some value, right? So if it's the same, I'm gonna go behind, and we're gonna say, right? I'm gonna go to replace here, and then we're gonna also check -1, right? We check -1. We say if. Oh, it's actually fine. We're gonna just say if index is equal, no, is larger than len dp. No, actually equal to len dp. Can I even do a binary search on empty? Because that would be 0. This one will be 1. I think we have to do 0 here. And then do 1 here. Right? And if it's equal to len dp, which means I have to insert the end, then we say dp.append h. Right? Else we say dp with a swap. So index is going to be the one we're going to insert, so that's like an in between, right? Then we're going to say else, elif, dp index -1 is not equal to h, which means it's not a repeat. If it's not a repeat, then we're going to say dp index, right? We're going to swap to h. And I'm going to return len dp. Oh. How? That's just 111. And then binary search 1 will give us 1. Oh, I'm appending. Okay. Can I do this? This has to go first. If this is not equal to h, alright, I think I have this problem before, that's why I have to do this. Index -1 is equal to h. Then we continue, right? We avoid this. And then we can just say else. Yeah, this one will pass. And this one shall pass. Submit. Yep, this one passed. Unbelievable. Okay, I failed today's challenge. I failed this question. I failed this problem. I check the solution, and below is the implementation of which solution did we go for? Here, this is the one we go for. I'll vote on this. Implementation, this implementation, the implementation of this answer. The basic idea is, yeah, I don't think ON squared is not going to work. I think maybe it allows for 9,000. How is ON squared not going to work? Maybe ON squared also works. But this one timed out. I sort it, and I go each one of them. Maybe this one will pass. Doesn't matter. This is the official solution, right? This is the official solution. The basic idea is to sort the envelopes based on width, and then based on width, ascending,
and sort height when width is the same, descending. Then the question becomes to find the longest increasing subsequence of length of height. A dumb DP solution for LIS is O(n) squared, which is likely TLE, but I'm not sure. The correct solution is solution for LIS for the length for length of LS is O(n) log n, as shown below. I have done LIS before, but I completely forgot about this solution. It keeps an array for the current LIS and constantly swaps in the smallest value encountered, the smaller value encountered. Thus, the LIS is not the correct LIS, but its length is correct. We basically try to keep LIS as small as possible. Thus, we are able to append more values to it. Appending is the only action that grows LIS. For a better explanation, check the solution, check this comment section of the solution for LIS. Okay, I'm gonna check the comment section. I'm also gonna put let's go put this one here as well. Solution, expand here. I mean, it's good enough for me to understand what it's trying to do. I think I can share, copy, so I'm going to do this. Okay. This one runs in O(n) log n, and I think I run it in 144 milliseconds and 92. So this is basically this longest increasing subsequence, right, with a little bit twist. All right. I don't think I'm gonna look into any other solution. This is good enough. All right. It's wow, this is the longest that I have ever done. We got stuck. So we got stuck yesterday. We got stuck today. We're not in a good stream. Anyway, that will be it for today. Adios.